Introduction. A conductor carrying a current will experience a resistive loss that gets converted to heat and raises the temperature of the conductor. A conductor, whose temperature is higher than that of its ambient, will dissipate heat and attain a steady state temperature when heat generated equals heat dissipated. The governing criteria for assigning a current rating to a busbar in a busbar system is the maximum current at which it attains a maximum temperature imposed by the specification. The current rating can be under a steady state or specified short time. The maximum temperature limit for the conductor is set based on the ability of the conductor and joints to retain the physical and chemical properties during their working life, the ability of the insulation system, in contact with the conductor, to withstand the temperature continuously without any degradation to its properties or life, meeting the health and safety norms. The heat generated by the conductor carrying a current I and having a resistance R at its operating temperature is I square R. Heat is dissipated from the conductor by conduction, convection, radiation. The ampacity of a conductor is normally assigned for a bare conductor or conductors in a defined configuration, at a specified ambient temperature and temperature rise, located indoors in still air. The assigned value is for DC or AC at a frequency of 50 Hz or 60 Hz. Very rarely do busbar systems operate under these ideal conditions. They are subjected to different manufacturing processes and service conditions such as varying ambient temperatures and atmospheric conditions, painted, coated, or sleeved, installed open or in a metal enclosure with air or gas as primary insulation, cast or impregnated with resin, installed indoors or outdoors, subjected to natural or forced air cooling. The mechanism of heat dissipation will vary for different busbar systems where the conductor is installed. Nevertheless, knowing the ampacity in an ideal condition, it is possible to predict with some fair degree of accuracy the rating of the conductor under different operating conditions. The heat generated by the conductor is evacuated by convection and radiation. In encapsulated busbar systems such as the sandwich bus, cast resin bus, and solid insulated bus, heat is evacuated from the conductor to the surface of the enclosure and insulation by conduction and subsequently by convection and radiation. Heat transfer along the conductor can take place when it passes through different ambient conditions, outdoor to indoor, or change in load through tap-off distribution. Conduction can also take place when different components such as laminates, flexibles, and breakers are connected in series. Each component will generate heat proportional to its resistance, including joints. Conduction will smooth the temperature distribution along the conductor. Copper and aluminium are good conductors of heat and will conduct the heat efficiently. Theoretically speaking, air can conduct heat. It is minuscule when compared with heat evacuated by convection and radiation, and is hence ignored. The effect of conduction along the conductor is not considered in determining the ampacity of the conductor. Conduction. Under steady-state conditions, heat transfer along a length of conductor operating between two temperatures is given by the equation displayed in Figure 6.1. The heat transfer rate is proportional to the area, difference in temperature, and inversely proportional to the length of travel. Convection. Heat dissipation by convection is very significant in a busbar system. It can be broadly classified under natural convection, forced convection. Natural convection is a phenomenon that occurs when a hot body is placed in unconfined, still air. When ambient air comes in contact with a hot surface, it gets heated. The air expands and its density reduces, causing it to rise along the surface. As it rises, it picks up more heat and the temperature of the air rises further and it gets lighter. It pulls the air from underneath, inducing a convection air current along the surface of the body, causing the evacuation of heat. The air film closest to the surface will be hotter than the air film away from the surface. Further, as the air rises and gets hotter, the efficiency of heat transfer gets lower. It implies that for a given ambient temperature and the surface temperature of the plate, for the same surface area, the cooling will be more for a plate of smaller height than that for a larger height. It is also evident that a vertical surface is more efficient for heat dissipation by convection than a horizontal surface. A conductor, when installed outdoors, will be subjected to wind in the horizontal plane. The efficiency of heat evacuation will depend upon the wind speed. For some busbar systems such as an isolated phase bus, heat from the conductor may also be evacuated by forced convection or forced cooling. The heat dissipated through natural convection per unit area is proportional to the difference in temperature between the hot body and the ambient to the power 1.25. The most popular shapes of the conductor in busbar systems are cylindrical and flat. The empirical formulae have been further developed considering the ambient pressure and the dimension of the body. The values of the constants for a few of the configurations are as follows. K equals 7.66 for vertical surface. K equals 5.92 for horizontal surface. K equals 7.66 for round tubes and cylinders. The above empirical formula, approximate as it is, assumes the object to be placed in still and unconfined air. This may be assumed to be valid for a velocity of air not exceeding approximately 0.5 meters per second or 2 feet per second. If the conductor is force-cooled by air, the heat dissipation per unit length will be proportional to the total surface area of the object, temperature difference from the ambient and the square root of the velocity. The mechanism of heat transfer by forced convection is very complex. Apart from the area, shape, and temperature difference between the body and the ambient atmosphere, the heat transfer depends upon the fluid velocity, viscosity, surface roughness, and several other parameters. Empirical formulae have been developed for various conditions defined by several non-dimensional numbers such as Froude number, Mach number, Reynolds number, Nusselt number, Prandtl number, Grashof number, Stanton number, Rayleigh number, etc. Radiation. The rate at which heat is radiated from a body is given by the famous Stefan-Boltzmann equation, which states that the power absorbed or dissipated per unit area is proportional to the relative emissivity of the body and difference between the fourth power of the absolute temperature of the body and the surroundings. The relative emissivity is a function of the absolute emissivity of the two bodies. The emissivity of a surface is its ability to emit infrared energy. It can vary between 0 for a shiny mirror to 1.0 for a black body. Absolute emissivity is the property of the material and its surface condition and varies with natural weathering. The emissivity of a metal varies with temperature. The coating of the surface can vary the emissivity of the surface. A darker shade of a coat will increase the emissivity. A dull or matte finish coat can further increase the emissivity. Matte finish has the effect of marginally increasing surface area and hence its ability to radiate more infrared energy. An interesting situation arises when the contribution of heat dissipation by radiation is comparable to or less than the contribution of heat dissipation by convection. The coating will introduce a layer of heat insulant between the conductor and the atmosphere, which will increase the thermal gradient between the conductor and the outer surface of the coat. In that case, the coating will reduce the current carrying capacity of the conductor. The coating will contribute to increased heat dissipation, only where the surface area is large and the operating temperature higher. A high emissivity factor of the surface will not only be a good radiator of heat, but it will also be a good absorber of heat. Solar radiation. Busbar systems that are installed outdoors are subjected to solar radiation. Apart from the ultraviolet radiation that affects the coat, they will be subjected to infrared radiation that contributes to the heating. Effects of solar radiation vary geographically and from season to season and time of the day. The radiation may be assumed to vary approximately in a sinusoidal fashion from sunrise to sunset. Solar constant, defined as the intensity of solar radiation on the surface normal to the sun's rays beyond the Earth's atmosphere, at a mean Earth-Sun distance, is approximately 1,334 watts per square meter, 135 watts per square foot. It has also been suggested that a wind speed of 4.5 meters, or 15 feet per second, could nullify the effect of solar radiation at noon. It has been mentioned earlier that the emissivity factor depends on the color of the coat and its surface condition. The absorption coefficient of various colors of paint are detailed in Table 6.1. It is a practice to install a solar shield for reasonable compensation when enclosed busbar systems are installed outdoors. Conductor shape. The conductor size, shape, and arrangement have been largely dictated by the minimum cross-section for the rated and short-time current for a specified duration, the maximum heat dissipation capability, the least skin effect ratio, the best profile to provide maximum section modulus to withstand electrodynamic stresses, the profile to align with equi-inductance lines to minimize the voltage drop. As will be seen later, it is the desire to keep the phase spacing to a minimum, while containing the short circuit forces to an acceptable limit and ensuring that it meets the specified insulation withstand capability. The least phase spacing will also result in minimum reactance, a very desirable parameter to keep the voltage drop and unbalance within specified limits. In the sandwich bus, busway, an ideal situation arises by keeping the conductors pressed against each other, where the proximity effect partially nullifies the skin effect. Conductor shape. There are a few popular sections of the conductor that are used in busbar systems. These are flats, channels, angles, and tubes. A combination of these profiles can be effectively used to optimize the ampacity rating of the conductor. The variation in the current carrying capacity is attributed to the combination of effective cooling and lower skin effect ratio. As will be observed later, the industry has, over a period, zeroed in on the specific shape of conductor for the type of busbar systems. These are based on standardization, ease of manufacture, cold working, coating, assembly, ease of installation, lower inventory, and ease of procurement. Low voltage bus duct, sandwich bus, and cast resin bus incorporate flat conductors. Medium voltage bus duct, with a rectangular cross-section of enclosures with copper conductors, incorporate flats, while those with aluminium conductors use channel. Medium voltage bus duct, with circular cross-section of enclosures, incorporate aluminium, tubular conductors. Medium voltage bus duct that envisage conductors to be given a coat of insulation, incorporate flat cross-sections as it is far easier to coat with uniformity on a flat profile, and make the overall cross-section of bus duct compact. The conductor in an isolated phase bus is tubular. Conductors, with channels in, box formation and octagonal cross-sections, had been used in the past. The conductor cross-sections, in high-voltage open bus and gas-insulated bus, are always tubular. The conductors in DC low-voltage high-current metal extraction plats are cast aluminium bars. In chlorination plants, it is thick flat copper bars. Capitalization of losses may alter the selection of the size of the conductor. Sleeving of conductors, if required, can be carried out only on flat and tubular conductors. It is far easier to extrude aluminium sections than draw copper sections. Most of the busbar systems with copper conductors are made of a flat cross-section as it is easy to control the flow while drawing and maintain uniform electrical and mechanical properties across the cross-section. Rating. The ampacity of a conductor can be arrived at from the heat balance equation. The heat inside the conductor is generated by the resistive losses and dissipated by a combination of convection and radiation. They balance out at the rated current. The results obtained from the above equation can only provide an estimate. The equations are derived for ideal conditions and far too many assumptions are made. DC ampacities will differ from AC ampacities by a factor of skin effect ratio. While calculating the ampacity of high-voltage open bus, incident heat from solar radiation and the effect of wind on heat dissipation by convection need to be considered. The skin effect ratio and proximity effect ratio cannot be exactly calculated. Convection and radiation losses are evaluated empirically. Effect of wind and solar radiations cannot be truly evaluated. Be. Heat from the neighboring conductors will affect the ampacity. Eddy and hysteresis losses in enclosure cannot be quantified. Ventilation of enclosure and its location, indoor or outdoor, will affect the heat transfer. Series elements in a run such as bolted joints, laminates, flexibles, generate local heating that are made smooth by conduction. To cater to several approximations, many derating and uprating factors are mentioned in the technical literature. These are, at best, first approximations. Over the years, most manufacturers have standardized the busbar rating based on the data available with them. Re-rating of busbars. When the ampacity of a conductor is known at a given ambient temperature and temperature rise, it is possible to predict, to a fair degree of accuracy, its ampacity at different ambient temperatures and temperature rise using the displayed relationship. For the same operating temperature, the ampacity for a different temperature rise will be proportional to the temperature rise proportional to 0.61. This method is accepted in the industry to validate a new design based on type-tested results. This methodology is more conservative when the test results are interpolated than when extrapolated. Short-time rating of busbars. In a power system, a short-circuit fault may occur causing disturbance to the normal operations. The fault current is likely to be several times higher than the normal current and depends upon the system parameters. These faults are detected by protective devices and cleared by isolating devices in a very short time. Relay settings determine the time duration of the flow of short-circuit current. and the conductor in the busbar system is expected to withstand the same without any permanent change to its physical properties. Copper and aluminium have different melting and softening points. The upper limit of the aluminium conductor, in air, is restricted to 200 C and that for copper, to 300 C. This upper limit for an insulated, encapsulated conductor, sandwich bus, cast resin bus, solid insulated bus, and cable bus, will depend upon the withstand capability of the insulation without any loss to its life or physical parameters. Since the conductor heating by the flow of current takes place within a short time, its cooling by convection and radiation need not be considered. The entire heat generated will increase the temperature of the conductor as in an adiabatic condition. It is important to note that both resistivity and specific heat are temperature dependent and vary significantly in the range under consideration. The resistivity increases by a factor of 1.6 between 20 degrees Celsius, 68 degrees Fahrenheit and 300 degrees Celsius L 572 degrees Fahrenheit. The specific heat increases by a factor of 1.08 for copper and increases by a factor of 1.075 for aluminium in the same range. Resistance, mass, and specific heat are material specific. Considering a unit length and substituting the appropriate value of resistivity, density, and specific heat, the relationship between the area of cross-section, the magnitude of current, and time duration can be arrived at. Time constant. When a conductor is energized with rated current, the temperature increases due to the heat generated from its initial ambient temperature. As the temperature rises, the heat is also dissipated from the surface of the conductor by convection and radiation. The rate of heat dissipation will depend upon its ability to evacuate heat by convection and radiation. The resistance of the conductor also increases with the increase in temperature, resulting in an increase in heat generation with the increase in the temperature rise. The conductor will attain a steady state temperature when the heat dissipated equals the heat generated. Time constant is the time taken to attain 63.5% of the maximum temperature rise. Thank you. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the founder-director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.